when a linear transformation between two vector spaces is an isomorphism, then it sets up a perfect correspondence between elements in the first space and elements in the second space. And then if we start with an element in the second space and we want to find the element in the first space that it corresponds to, that map is another linear map, and that's called the inverse of the first linear transformation. So if T from V to W is an isomorphism of vector spaces, then there is a perfect matching of elements in V and W given by little v in the first space corresponds to whatever T of V is in the second space. And every element W in the second space is T of V for some element V in the first space. And then we define T inverse from W to V, so going backwards, to be the map that sends W to whatever element V satisfies T of V equals W. There's only one of them in V. The coordinate version of this is if we fix bases B and C of V and W, then the and let the matrix of T be A. The matrix of T with respect to B and C is A. Then the matrix of T inverse with respect to C and B, now W is going to be the first space and V is going to be the second space. So we've got the second basis and first basis. So that's just A inverse. So for example, let's let V2 be polynomials of degree at most 2. And let's let W be upper triangular 2 by 2 matrices. Then one isomorphism from V to W. So one obvious isomorphism from V to W is we take a polynomial a naught plus a1x plus a2x squared and map it to a naught, a1, a2 on the upper triangular part of a 2 by 2 matrix. Now this is not the only isomorphism. In fact, there are infinitely many. Isomorphisms from any space to another space which is isomorphic to it. So between two isomorphic vector spaces. So let's look at another one so that we actually have an interesting matrix to go along with the map, and we can invert it. So another isomorphism actually V2 to W I meant to say here, from V2 to W is we can take A0 plus A1x plus A2x squared and map it to the matrix whose entries are A0 plus A1, A1 minus A2, and A0 plus 2A2. And 0, of course. So let's let T be this transformation. So the matrix of T with respect to the bases, we'll pick the natural bases, 1x x squared and 1 0 0 0 0 1 0 0 0 0 0 1 is, let's see, so we need to know where 1 is going, where x is going, and where x squared is going, and then we'll express each of those evaluations in terms of this basis. So T of 1 is T of 1 plus 0x plus 0x squared. So we've got 1 plus 0, 0 minus 0, 0, and then 1 plus 2 times 0, so 1. And the coordinate vector is 1 0 1, because that's one of these plus 0 of those plus 1 of the third thing. And then T of x is T of 0 plus 1x plus 0x squared. So we have 0 plus 1 here, 1. 1 minus 0 there, so another 1, 0, and then 0 plus 2 times 0, so 1 1 0 0. That has coordinate vector 1 plus 1 1 0. And then T of x squared is T of 0 plus 0x plus 1x squared. So 0 plus 0 is 0. 0 minus 1 is negative 1. And then 0. And then 0 plus 2 is 2. So we get the coordinate vector 0, negative 1, 2. So the matrix of T is we just take those coordinate vectors and put them in the columns. 1 1 0, 0 negative 1 2. So the natural question is, what's the inverse of T? And how do we find it? Well, I think the easiest thing to do is to find the matrix of T, which we just did, invert the matrix, and the inverse matrix will tell us so we'll use the inverse of the matrix of T to find T inverse. Alright, so I inverted this matrix already, so you don't have to watch me go through all the steps. Let's say this matrix is A. So the matrix of T inverse is A inverse, which turned out to be 2, -2, 1, -1, 2, 1, and -1, 1, 1. So when we say what is T inverse, so what does T inverse do to our typical element here? Let's say A, B, C. So this is our typical element that's upper triangular. And if we know those three numbers, we should somehow be able to use that to figure out what polynomial this is going to correspond to. Well, we can just apply this matrix A inverse to the coordinate vector ABC. So whatever it is, it has coordinate vector 2, -2, 1, -1, 2, 1, -1, 1, 1, A, B, C, which is 2A minus 2B plus C, -A plus 2B plus C, minus A plus B plus C. That's the coordinate vector. And thus it is 2A minus 2B plus C plus -A plus 2B plus C x plus -A plus B plus C x squared. Oops, I see that I copied my inverse matrix down wrong. That inverse matrix should have 2, -2, -1 in the first row. And that means that we've got 2, -2, -1 here. And that means that I've got a minus C in the first row. But that's the only change. So 2A minus 2B minus C is the constant term of my polynomial. Okay, now let's check that if we apply the linear transformation to this polynomial, that we actually get this matrix A, B, C above the diagonal. Alright, so our linear transformation was T of A0 plus A1x plus A2x squared equals the matrix A0 plus A1 here, and then A1 minus A2 there, 0, and A1 plus 2A2. So T of this polynomial, 2A minus 2B minus C plus -A plus 2B plus C plus negative a plus b plus c. This is x, and that's x squared, equals, alright, so we should take constant term plus coefficient of x, add them together, and get this component. So 2a minus a is a, negative 2b plus 2b is 0, negative c plus c is 0. Okay, so a is that first component, that's good. And then to get this component, we should take the coefficient of x minus the coefficient of x squared. So negative a minus negative a is negative a plus a, which is 0. 2b minus b is b. And then c minus c is 0. So we get b there, which is good. 0 here. And now coefficient of x plus 2 times coefficient of x squared. I'm sorry, this should be a naught here. That was our original map. So constant term plus 2 times coefficient of x squared. So 2a plus 2 times negative a is 2a minus 2a, which is 0. Negative 2b plus 2 times b is negative 2b plus 2b, which is 0. And then negative c plus 2 times c is negative c plus 2c, which is positive c. So indeed, this is the inverse, well, this map is the inverse transformation, and we can see that if we apply t to this, then we get back to the matrix ABC. The end.